MCTDH, you could probably treat 50 nuclear degrees of freedom. This, of course, is a bit flexible depending on the actual fine details of the calculations. Using a standard grid-based approach, you're going to be lucky to do much more than 4 or 5 degrees of freedom. There is also what's called a multi-layer variant of the MCTDH, which actually, again, depending on the actual details of the calculation, can treat about 1,000 degrees of freedom. And I think the important thing to point out at this point is that 50, 1,000, okay, there's a big difference in the number, but this now shifts the emphasis on getting the model potential energy surface. Maybe some of you can, but I certainly can't think in 50-dimensional space. So we now have methods that can treat large systems, but we shift the emphasis on getting the potential energy surface. Just one quick slide. MCTDH in its standard form doesn't include the effect of temperature. And so if we want to include temperature, we have to switch to so-called density matrix formulation. Here we have rho MCTDH. And clearly in the context of this conference, the fact that the first word is thermally tells us that we do need to incorporate temperature. So we have to start with an initial wave function which represents the thermal distribution. Within MCTDH, everything mathematically stays essentially the same. We can still get a rigorous solution. The one thing, and without going into the maths, is that the dimensionality of our simulation formally doubles. So if we had a model that had 5 degrees of freedom, when we do the density matrix formulation, it now essentially has 10, it's the same as the effect of having 10 degrees of freedom. So this does limit the system size that we can do. And this is certainly a challenge. But the important thing, as I said, is we have an approach that can treat many degrees of freedom, and we have to find a way of calculating the potential energy surface. So what we essentially need to do is we need to develop a model Hamiltonian. There are two kind of main ways of doing this. We can either parameterize this from experiment. So if anyone follows the work on the light harvesting complexes, so the Fenner-Matthews-Alton complex, generally what is done here is they have a form for their Hamiltonian, for their potentials. They have a range of parameters that are free to vary. They set these parameters and they calculate the absorption spectrum. And then they compare that absorption spectrum to the experiment. And when the absorption spectrum matches, they say, okay, this is a good representation of our model. We can now understand about photosynthesis using this model. Okay, this is a nice approach. I would say the one limitation of this is something like an absorption spectrum can be a fairly big blobby thing. It's not too difficult to simulate a big blobby thing with the right parameters. So you always have to be careful here. Alternatively, and this is the approach that we're going to take, we can use first principle calculations. So we can do quantum chemistry to calculate a potential, and then we can get the parameters for our model Hamiltonian from this. Okay. The important thing for excited states is that when you run your favorite quantum chemistry in your favorite quantum chemistry code, you will get the adiabatic result. And what we need is, as I said at the end of the last lecture, is this diabatic representation. And converting between the two is not particularly straightforward. So converting from the adiabatic to the diabatic basis is very challenging. Converting from the diabatic to the adiabatic is actually a lot simpler. We can just do a diagonalization of the Hamiltonian. And that's what we take advantage of in this approach, which is the vibronic coupling Hamiltonian. So this was developed by Nancy Siedebaum, Hans-Dieter Meyer, Horst Koppel in the 1980s, and it's more or less stayed untouched since then. And this approach is what we call diabatization by ansatz. So we have essentially a Taylor series for our Hamiltonian, and each has various terms. And so the first, the 0th order Hamiltonian is the harmonic approximation for the potential. So this approach is only really valid for small amplitude distortions. So if you're interested in photophysics, then it's great. If you're interested in photochemistry, where you have some dissociation, and then this will definitely not work. We're looking at small amplitude motions around the initial starting point. So the first thing we do is we approximate the shape of the potential as a harmonic oscillator. The 0th order coupling matrix, W0, contains the excited state energies at the geometry that you're starting at. So this could be, say, the ground state equilibrium geometry. So in the first case, we just have, if we have a number of states, we just have a few harmonic oscillators. And then this first term shifts these potentials to the relevant excited state energies. And then after this, we have sort of the first, second, third, and fourth order coupling matrices. The first order coupling matrix is generally the most important, and if we stop the sum at here, we call this the linear vibronic coupling Hamiltonian. We go to the second order, we call it the quadratic vibronic coupling Hamiltonian. This matrix has on and off diagonal elements. The on diagonal elements shift the minimum of the potential with respect to the ground state minimum that you define. And so if you, at the first point, you have two harmonic oscillators that are the minimum are at the same point, and if you have a structural change in the excited state, then one of these on-diagonal coupling terms will shift that minimum so it represents the structural change along that degree of freedom. The off-diagonal elements of this matrix couple the two different electronic states. So here, this is responsible for the non-adiabatic coupling, so this allowing the wave function to flow from one state to another.
So just to be clear, your harmonic functions are harmonic functions of the zone state.
Yes, what? So around, they don't have to be the zone state, they usually be ground state, but they don't have to. Okay, so this is a schematic representation of what I've just said. These points, and actually practically how we do it, because in reality what we do is, this is some arbitrary degree of freedom. It could be a normal mode that we're interested in that's particularly important. And these dots are the quantum chemistry calculation that are just extracted from whatever code that you want to use. And this is the 0th order, the H0 term, in which we have just a harmonic oscillator with the frequency associated with that normal mode. And so we essentially take this Hamiltonian and we perform a fitting procedure. So we guess, here it's just the frequency term, we guess the coupling matrix, its elements, we then diagonalize the Hamiltonian to get the adiabatic basis, and then we compare it to our quantum chemistry. And we see how well it fits. And then we iterate until we have the best fit. So initially we have a bunch of states that are just harmonic oscillators. We then add this 0th order coupling term, which shifts a couple of these surfaces to the excited state energy at the 0 point that we have defined, so the minimum. And then we add first order coupling. So this actually splits these two states. So actually the reason that these are split is because of non-adiabatic coupling. You can see here that this fit actually is quite nice, very close to the equilibrium geometry, but at further displacements, then higher order terms become important, and so we now include also the fit of second order terms, which then give a good agreement between the model and the quantum chemistry. So at this point we would say that we have good agreement, and the parameters that we extract from our fit we can now use in our model Hamiltonian and perform the dynamics. In this fitting procedure,
just to be clear, so if you would have a kind of, say, let's say a rotation or something like this, you're doing calculations for all kinds of angles, so to say, for this degree of freedom, so to say, and this gives you the different points.
Exactly right. One thing to bear in mind is that as you increase the order, as you go to higher and higher orders, the number of terms that you have in your Hamiltonian increases. And obviously the number of free parameters you have makes it easier to fit. Okay? But also means it's easier to get nonsense. And so generally the procedure that we do is always try and fit to lowest order, and then once we've achieved the best fit at one particular order, is to freeze all of the parameters associated with that order, and then move on to the next term to refine the model. So in this way we're not essentially shoving 10,000 free parameters into a fitting procedure and coming up with something that is complete nonsense.
Tom?
Yeah.
Can you only do it for one mode at a time, or can you actually look at how two modes interact?
You can look at 2 modes interact, yeah. You would calculate the potential along both of those modes simultaneously. Yeah, you can do that, yeah. In principle, there's no reason why you have to stick to the modes. You can just calculate thousands of random points all over your potential and then fit it that way. You can do that. Okay, so just to be aware of, the Hamiltonian is based upon normal modes, and so generally only small amplitude motions. You can use it for photophysics, where you're returning to the state you started. Photochemistry is going to be more challenging, but if you're trying to optimize on the devices, if you've got photochemistry going on, you should probably worry more about that than actually with your model work. you have to take care in selecting the most important normal modes. And in this way, various levels of quantum chemistry can be useful. If you need some very high level quantum chemistry method, that each point takes a day to calculate, you may want to consider using a cheaper method to scan the potential to begin with to get an idea of what's important, and then go to, once you've identified this, then go to the higher level of theory. Okay, actually this relates to exactly what Andy just described. Cuts along a single normal mode like this, which doesn't describe how 2 degrees of freedom couple in the motion. And so you would have to actually incorporate this as well. This I've actually more or less or almost said in the fact that we're doing reduced coordinate space, and so we won't get things like intra-vibrational redistribution. So if we've got a lot of energy going into the vibrations and we want to understand how this is distributed throughout the molecule, this is not going to be captured. In an atomistic way, environment effects are not included. You can include this in a phenomenological way, okay, that's something else. I think the other important thing to mention is that because you are fitting your potential energy surfaces and you're getting parameters out, one of the things you should always do with your model is check how dependent the results on these parameters are. Okay? Fitting is fitting. You're not necessarily guaranteed to get the right answer. And so if you perform a fit and you find that some one particular degree of freedom has a huge non-adiabatic coupling, and you run your dynamics, and it gives you this exciting new phenomenon that you haven't seen before, check how sensitive the dynamics are to that parameter. If you can vary it by 50%, and okay, it just changes the amplitude, it doesn't actually change the dynamics that's going on, then you're probably fine. If you take one of these parameters and you change the 4th decimal place, and it completely changes the outcome of the dynamics, then you should really wonder whether you should actually be assigning any kind of weight to this at all. Okay? So just bear in mind that you are fitting. There are limitations to this model, and you have to be aware of those when performing the dynamics.
I actually have a question, because if I understand correctly, for each degree of freedom you have to do quite a few points on the surface calculation. And if you really want to take the cross-correlation into account between different degrees of freedom, this also scales exponentially again. Yeah. So if you really also have to have a imagination of how this cross-coupling really is, because I mean you cannot calculate for 5 degrees of freedom, you would be ending up with, I don't know, 100,000 of calculations.
Yeah, so only, can I write on the wall? In that sense, we take advantage of the fact that the diabatic potential is generally smoothly varying. See if people can see this. Okay, right. So, this is your nice 2D potential energy surface. Look from the top up, and you're perfectly right. If you have 10 points along here and 10 points along here, you have 100 points to calculate. What we would actually do is this set of calculations. So you'd have 10 along here, 10 along here, and then the coupling between them is the diagonal line, so that's another 10. So instead of 100 calculations, we'd have 30, and because the diabatic potential is smoothly varying, we can interpolate in this region
You've got a linear interpolation, so to
exactly.
say, and that should be
Exactly.
fine.
That should be absolutely fine. But you know, you're right. If you want, which is why I said if you need to use a very accurate quantum chemistry where each point takes a day, then yeah, so there are. So you can also get a guidance of what's important. So, for example, if you were looking, let's say, for TADF, you were interested in the S1 state, the T1 state, then, and you started from the ground state geometry, you could also optimize your molecule in the S1 state, the T1 state, express those geometries in terms of normal mode coordinates, and then get an idea of what the structural distortions are. Generally also lower frequency modes are going to dominate, and so there is, you can simplify it to some degree. Okay, so this is an example that we did about 3 years ago. So this is a copper phenanthaline complex. This was studied in the probably 70s by Macmillan's group. And in the ground state, the two phenanthaline ligands are perpendicular. And when you photoexcite your system, you go from the ground state to a metal to ligand charge transfer state. The copper 1 becomes copper 2. And you get this pseudo-Jahn-Teller distortion. And so what you get in the excited state is a flattening of these ligands. And what we were interested in is that the two experimental groups, the group of Tahara and the group of Chen in Northwestern, had done ultra-fast measurements on this. They'd got exactly the same timescales, but assigned them completely differently. One had assigned to ultra-fast intersystem crossing, and the other had assigned to the structural distortion associated with these ligand moving. And so in exactly the same way, what we did was we calculated the potential along various degrees of freedom. It's actually dominated by 2 degrees of freedom. This mode 8, the 8th normal mode, is actually the breathing mode between the copper and the nitrogen, the copper-nitrogen bond length. So we get a slight structural change in the excited state. And then this 21 is this Jahn-Teller distortion associated with the flattening of the ligands. Okay. So we calculated the potential, we fit the model. It actually had 8 degrees of freedom, the other ones I haven't shown. And we performed the dynamics. So this is, so here, the grey filled area is a Fourier transform of the wave packet dynamics observed by the group of Tahara, these coherent oscillations in the excited state. So this is the normal modes that are active. And the red bars are the modes that we identified to be important in the excited state. And so we have reasonably good correspondence of modes to peaks in the spectrum. And so we initially excited the S3 state, which is the optically bright state, and we performed the quantum dynamics for a picosecond. The S3 state decays very quickly, and you see decay down into the S1 and the S2 states, which are almost degenerate. They're split by this rotation. But within the picosecond of the dynamics, they're more or less in an equilibrium. This was when we didn't consider the triplet manifold. So we didn't incorporate the ability to undergo intersystem crossing. If, on the other hand, we include the spin-orbit coupling, the dynamics looks like this. The decay of the singlet state is more or less the same. The initially excited state is more or less the same. But now, within the first picosecond, almost 80% of the wave packet is in the triplet state. So we can say that this is ultra-fast inter-system crossing. So yeah, we had 8 degrees of freedom and 5 states. And I think the thing to illustrate with this is that you will often hear people say of quantum dynamics, oh, one of the limitations is you can only do small molecules. And you have to be careful here. You can do small models, okay? 8, 10 degrees of freedom. Doesn't mean you have to do small molecules, especially in the things like organic electronics. You generally want quite rigid molecules, and so the number of degrees of freedom that are important are quite small, and so you can actually generally represent them very well with a simple model. To give you a contrast, my PhD was on the photochemistry of benzene. So that's what, 12 atoms? And this was a hell of a lot harder than this molecule. Essentially because all of the degrees of freedom coupled, you had to include every single one. It was a lot more complicated than addressing this. Yeah.
So to understand correctly this population stuff, so this is a dynamics of this state which goes from one excited state to another excited state to the ground state.
Not to the ground state. We don't include the transition back to the ground state. This is basically within the first meter.
So basically you consider the states which intercross, right? And there is no radiation here. There is no coupling to
So we haven't incorporated that in here. No. We can. So obviously, as you want to try and get closer and closer to experiment, you could actually put in your laser light, pump laser, to excite your wave packet. You can do that. We've done that for other systems. It basically, in this case, it had no effect. It became essentially the same dynamics. But there's no reason why you can't do that.
Could you explain the meaning of different curves?
Okay, sorry. So the black curve is this initially excited S3 state, so third excited state. The purple line is the S2 state. So what this is telling you is that as this decays, the population leaves the S3 state and then goes into initially this S2 state. But because the S2 state and this S1 state are very coupled, then very quickly goes into the blue line, which is this S1 state. So it's telling you how much of the wave function is in certain states. And so it's exactly the same here, but this red line now represents the triplet.
This is, so somewhere you have the dissipation, right? So, or the energy is not conserved.
No, the energy is conserved. So part of the reason that we go to a picosecond, so actually if we, which I would just like to say, is that we dump, so this is about an electron volt higher than these two states. And so we have very vibrationally hot wave packet in the S1 and the S2 states. If we take the oscillations of the wave packet and compare it to what Tahara saw, for the first 500 femtoseconds, the agreement is really apparent. For the second 500 femtoseconds, you start to see a phase shift and things aren't agreeing so well, and that's because we've not got the dissipation. We've only got these 8 degrees of freedom, where the molecule has 165. After a picosecond, the wave packet motion really doesn't look anything like. It's really starting to look quite different. So that's why there's new.
Tom, you mentioned that you include spin-over coupling. Does this mean to just include coupling of a higher lying single with the triplet state, or how could you express that? Including spin-orbit coupling.
the spin-orbit coupling is included in exactly the same way as the non-adiabatic coupling. So